Let's hope this works. Okay, I think we'll start now. So I'm going to be giving 3 lectures now, Monday, Tuesday, and Wednesday, and then on Thursday is going to be another talk by Professor Arthur Mariano, and then Friday I'm going to be talking once again. So there are going to be 4 lectures on waves, and I'll tell you how I arranged it. The first 3 are actually concerned with what we call the beta plane, or waves of the geophysical fluid dynamics in Cartesian coordinates, basically. By the way, how many here are geophysicists? None? Are you ashamed to admit it? No, okay. So you're all mathematicians. Okay, so I have to introduce you to the waves. I thought it's going to be only partial exposition of the wave dynamics. So I'm going to be talking about 3 aspects of wave theory, simulations, and observations. So they're more or less going to be split into these 3 first lectures. And then in the 4th one, which is going to happen on Friday, I'm going to be talking about waves on a sphere. And as you'll see, the sphere is a very, very complicated geometry that complicates the terms very, very much. So let's start with the theory on the beta plane. And this is unexpected. Okay, so the first will be wave theory in Cartesian coordinates and the theory, okay? So the theoretical part of waves in geophysical fluid dynamics and the exposition of the what we know, say, in textbooks, okay? As you'll see, there is very little advancement beyond textbooks. So what we know in the community is not much more than textbook material. And I'll just start with the review of what you can find in textbooks, just because now it turns out you're not geophysicists, so nobody knows about it. If you know a little bit, then that's fine. And then I'll tell you a little bit how we can make advancement by transforming the equations into a Schrödinger equation. And what the better place to do it than right here in the Schrödinger International Institute. And then the rest of it will be dedicated to solutions. It's not going to be very thorough, but at least give you the highlight of how we solve this equation. It's not simple equations, even the Schrödinger equation. Then the second part will be numerical simulations and how we know that these solutions are actually relevant, at least to numerical simulations. And then the last part will be observational evidence for the existence of these new wave types. Okay, so that's the plan for more or less from between here and Wednesday. By the way, if you have any question, please raise your hand, ask me, because I prepared material, but it's not really required that I finish everything. If I finish part of it, some of it, most of it, that's good enough. Okay, so the platform we are working on is rotating shallow water equations. Let me spend a few minutes on explaining to you what these equations represent. So this is what we call the momentum equations. They show you the change in momentum. So V is the horizontal velocity. K is a perpendicular vector. Okay, so if you think about V on a plane, then K is perpendicular to it. If you think about the sphere, then K is the radial direction, and the sphere is the tangential or the plane. F is the Coriolis parameter or Coriolis frequency that really complicates the dynamics much, much more than you are used to in, say, regular fluid dynamics. And the pressure gradient is given by the gradient of the height. Okay, G times eta. I'll explain to you in a minute what exactly eta is and why G is the force. But these two scalar equations, or one vectorial equation, is complemented by this equation, which represents the continuity equation. We call it continuity because it expresses the conservation of mass. So mass is never destroyed, and therefore the change in the height of the fluid can only occur because you have divergence or convergence of the fluid. So think about two columns of water that are moving towards one another, then the height will go up. And if they move away from one another, then the height will go down, the surface of the fluid. This equation, the continuity equation, represents the conservation of mass. And basically, G can be replaced by what we call the reduced gravity. So think about it as a parameter, if you will. And H is the mean thickness of the fluid. So if you want to look at a pictorial demonstration, think about the flat bottom, and here you have eta, okay? And there is a mean height, we call it H, okay, constant. We'll leave it as constant. And the changes in the height are caused by the convergence and divergence of columns of fluid that are moving towards one another or away from one another. So these are the linearized shallow water equation. The acceleration here doesn't take into account the fact that there are advective part to the acceleration. And this is a very simplifying assumption that the nonlinear terms associated with the advection are indeed small, and it's usually true for very small velocities, okay? And how small the velocity should be is a bit unclear from the outset, but let's think about it as a way of starting to address the problem when we talk about linear dynamics, okay? So linear wave dynamics is linear here, and just to remark a few more words about the linearized shallow water equations, then it's essentially Euler equations for a compressible gas with an equation of states in which the pressure equals rho squared. So if you think about it as rho, about eta as rho, then the gradient of the pressure gradient is given by rho itself. So P is like the integral of rho, and therefore P is proportional to rho squared, okay, up to a factor of 2 here. But if we knew how to solve Euler equations for a compressible gas with this equation of state, we probably would have had much better life with our linearized shallow water equations. It represents the layer thickness is such that the horizontal velocity, v is the velocity along the surface, is assumed to be independent of the vertical direction, which is an assumption that simplifies things. The other thing is we linearize it just because we're not smart enough to solve nonlinear problems. And if you solve nonlinear partial differential equations, then all kinds of weird things happen. We don't know how to solve it. There are shocks and weak solutions. So we adhere to the simple structure of linearized dynamics. We can understand waves in a linear system by applying very simple concepts like frequency, like wave number, like propagation, amplitude, et cetera, et cetera. So this is why we study the linearized shallow water equations. Again, when we say shallow water equations, we mean with rotation. So when the Coriolis frequency, this F is the Coriolis frequency, is a determinant element in the dynamics. Okay, so how do we further simplify the equations? We first of all take those vectorial equations and we pretend that we live on a flat Earth. Now, it has been known for about 2,500 years that the Earth is not flat, and hard to believe it when you read books like Pulaski's or Vallis's or any of the GFD books, because they have out of the 1,000 pages, maybe 2 that that involves spherical coordinates, as if nobody knows that the Earth is a sphere. So we know that it's a sphere, but as you'll see if you come on Friday, it's a very, very difficult task to study these equations on a rotating sphere. But for now, what we do is the Coriolis frequency is given by 2 omega. Omega is the frequency at which the planet or the sphere rotates about its own axis. Okay, so if you live on Earth, you rotate, and we know what the period is, and therefore 2 times the frequency times the sine of the latitude gives you the Coriolis, the scalar called Coriolis frequency. And what we do is we attach a tangential plane to the sphere, okay, a plane that's tangential to the sphere at some latitude, and we live on that plane. Okay? We forget about the sphericity of Earth. Now, on that plane, we can have 2 approximations for the Coriolis frequency. One of them is that the frequency is constant, as if there is no change in latitude when you move north and south along the plane. This is a very crude approximation, and it's called the F-plane. Why is it the F-plane? Number 1, it's a plane. Number 2, F is assumed constant there. You can also take the sine phi function and develop it in power or Taylor expand about that latitude at which the plane is tangential to the sphere. And if you expand it to first order in phi, then you get F0 plus beta y, where beta is given by cosine phi 0 over a, just regular Taylor expansion. And when we consider the variation of F along the meridian on that plane, we call that plane a beta plane. Okay, so when you read it, it's if there are 2 planes. There are no 2 planes. It's 1 plane, but what we assume on F along that plane determines whether we call it the F plane or the beta plane. It's as bad a nomenclature as you can think of, but this is what it is. Just to mention, mathematicians usually don't use latitude, but oceanographers and meteorologists are attached to geography. And therefore, the equator is latitude 0, and the poles are 90 degrees plus in north and south. And therefore, our meridional direction goes from 0 to plus pi over 2 or minus y over 2, whereas the mathematicians usually like to take theta to be 0 going to pi over 2 and then pi. But just co-latitude versus latitude, simple transformation from one to the other. Perhaps as baffling is the way we denote the longitude, what's called the parallel. Okay, if you move parallel to the equator, usually I think mathematicians take phi to be the longitude, but again, since phi is taken for the latitude, then lambda, which is longitude, Greek letter for L, is now taken to be the longitude. So this is just nomenclature, okay? So on that plane, the del operator is simply d dx d dy, which is really very simple, okay? As simple as it can get. And V has 2 components. We call them U and V. And it's very easy to distinguish between them because one of them will be a vector and the 2 components will be scalars. Okay, so this is just to set the language. Okay, so when I call V is a 2-dimensional vector, not a 3-dimensional vector. And the directions are on the plane are X and Y in the north, X and Y, and the perpendicular direction, the radial of the sphere is denoted by Z, and the unit vector is K, which is what I showed you in the previous slides. Are we set on just the names and the nomenclature? And okay, we are with me. Okay, terrific. So now if I just take the vectorial equation that I had before, and I just transform them to the scalar form, again, using these coordinates, then you see that for u, the eastward directed velocity, this is acceleration. This is, again, the Coriolis frequency, which is latitude dependent, latitude along the plane, not latitude on a sphere. And this is, again, the pressure gradient. If you have more water here, then the pressure gradient forces water columns to move from high to low. That's why we have here the minus sign. Okay? Where the water level is high, then water is pushed away from it. So far, so good. This is just the continuity equation where I took the del to be du dx plus dv dy. So these equations can be solved okay, this is sigma here. I'm sorry. I apologize. So if you now look at the textbook, and the textbooks are using methods of solutions that are unorthodox, say, in some way. We'll deal with them with a little more accuracy later on, so I won't spend too much time on it. But what I want to show you here is that there are basically three wave types that we know of. The first one is these two, the pair of waves called Kelvin waves. And Kelvin waves are non-dispersive, i.e. the frequency is a linear function of the wave number. So this is omega versus k. This is taken from Podolsky's book on geophysical fluid dynamics. And these waves are non-dispersive. C, the phase speed, is constant. Okay? And the phase speed of these waves is exactly the phase speed that we know from non-rotating fluids called the gravity waves. Okay? So you just drop a pebble in a puddle, then the waves that will move away from the center of where the pebble touched the surface of the fluid, they propagate at this speed of square root of gh, where h is the thickness of the puddle. The same thing happens with a tsunami. If you have an eruption underground, ocean depth, and again, this is the speed of propagation of those waves. And as you can see, there is no F, there is no rotation in the dispersion relation, but F does appear in the eigenfunction. Remember, whenever we solve an eigenvalue problem, we have an eigenvalue and an eigenfunction. And F does appear in the eigenfunction. So even though it appears as though the solution is of a non-rotating fluid, it does belong to a rotating fluid. Another interesting thing is that V is equal to 0. Again, we'll talk more about it later on in the theory. The other wave types are these two fast waves. Okay? And the fast waves called inertia gravity waves, or sometimes called Poincaré waves, especially if you come from France. They give honor to Poincaré, Henri Poincaré. And you can think about them as Pythagorean sum of the two frequencies in the problem. One frequency is the Coriolis frequency, this F, and the other one is the frequency of gravity waves. So you take the two of them and you take the combined frequency, it's just the Pythagorean sum of the inertial frequency squared and the gravity wave frequency squared, and this is a simple way of combining, not linearly, but combining the two waves that generate those inertial gravity waves. And they are fast, because remember, this is very fast and this is even faster. And the third wave type, which you can see here, is perhaps the most interesting because it doesn't have a counterpart in non-rotating fluid. And we call them planetary or Rossby waves. Carl Gustav Rossby was the first one to study them. And they're named after him. In the literature of the first half of the 20th century, they were called first type and second type of waves, okay? So first kind and second kind, if you encounter, it's 1 and 2. And what's Interesting about them is that they propagate only westward. So remember, the phase speed is in the x direction, and x is positive eastward. So if they have a negative phase speed, that means that they propagate westward. Okay? They are linear with beta, with the change in the Coriolis frequency. Just to look at the dispersion relation, this is how zoom in on the dispersion relation of these waves. This is mode n equals 0, n equals 1, and there are infinitely many of them. Just to say a few words about them, this is the exact dispersion relation. So you see, this is sigma. If you computed C, then you divide by K, it becomes just beta in the numerator. And then in the denominator, you have K squared, the zonal wave number, the wave number in the x direction, plus this is something, if you have a channel of length L, then the wave number in the meridional direction is quantized because you need to satisfy the boundary condition. And so they, instead of having L squared here, the L is quantized. Here you have this term F squared over GH that we usually call 1 over the radius of deformation squared. I'll touch again on it in a few moments. And in the meridional direction, the wave number, of course, is quantized, as you can expect in an eigenvalue problem that has two boundary conditions. Like in a very simple eigenvalue problem, you have discrete modes. They only propagate westward, and they are derived from vorticity. I won't go into the vorticity because we're adhering to shallow water, rotating shallow water, but they are, since they are vorticity waves, sometimes they are called rotational or non-divergent. They can, if you cut away the divergence, and if it's really non-divergent, then they don't exist. So it's, when you read those books, especially those of you who have mathematical sensitivity or sensitivity to mathematics, say, wait a second, so it's small but non-zero. So what happens, what exactly defines how small is small if it cannot be zero? Or what exactly makes it non-rotational? It seems like a little bit of too much of hand waving without a more concrete way of looking at it. The only additional thing I would like to point out is that we have F beta here and F here, but the F here is F0. Okay, this is a constant in the dispersion relation. You only have constant. Yes. Oh, I'm not tracking the vorticity. I'm not saying this theory that I'm going to present is not vorticity. I'm just saying they can be derived from vorticity. Okay? If you look at those textbooks, I'm just displaying to you the elements of what we know in linearized shallow water equations, rotating shallow water equations. Okay? No, I don't think it has to do with irrotational in the mathematical sense. It has to do with the fact that they originate from the vorticity that encapsulates the rotation of Earth, whereas divergence ignores the rotation of Earth. Okay, so the rotation here is not what the fluid dynamicist will call rotational aspect of rotation. So again, it's another example of where the term is misleading in some sense. But here, all I meant to say is that if you look at the equations in which divergence is zero, you will get the Rossby waves, a subclass of Rossby waves, but you will get them. Okay, that's what I meant. And that's why they are called rotational. They have to do with vorticity, not with what you would call rotational, okay? But what I'm trying to say is that if you look at the dispersion relation, and of course, if you look at the eigenfunctions, you see here two constants, beta, which we know what it is. It's the gradient of f, and you have here f, which we interpret as f0. So it's as if the equations have two constants, okay, f and f0 and beta, but there is no y-dependent coefficient in the equations. But the equations do have a y-dependent coefficient. So somehow, again, it's another it's doing math with hands, you know, waving hands. So I'll try to fix that, and I'll just point out three subtle issues associated with the mathematics of how, or the math aspects of how these equations, these waves are derived classically. The first one, when you have a y-dependent coefficient in your equations, you never have solutions that behave in a harmonic way in the y direction, okay, in the direction where the coefficient is varying. Sine and cosine wave, or sine and cosine behaviors, typify an equation with constant coefficients. They don't typify an equation that has y-dependent coefficient. Indeed, as we saw in the solution behaves as though there is f0 and beta, but not f0 plus beta y. So somehow, again, we managed to come up with a theory that ignores the fact that you have a y-dependent coefficient, and therefore you cannot decompose it simply by sine and cosine eigenfunctions. It leads to another, perhaps, I would say 1b, if this is 1a, and that is, if I wanted to inquire about the accuracy of this model, there is no way I can gauge whether the results I got are accurate. And what is the accuracy? If I'm willing to sacrifice, if I'm willing to settle for a 10% accuracy, then what does it mean? What values should f beta and f0 be in order for the result to be accurate for, say, up to 10%? Just have to trust me, or to trust Podolsky or values. That is good. It's very good, but nothing more than that. A somewhat more subtle issue that has to do with the derivation of these waves in the classical books is the fact that if you take f0 to be 0, and that can be easily done by moving our plane to the equator. There's nothing special about placing our tangential plane, say at 45 or 30 degrees latitude or 60 degrees latitude. You can also move it to the equator. In the equations, f0 doesn't appear in a singular form. It doesn't imply singularity or qualitative change in the equations. But if you send f0 to 0, then you do not get the results that we know when we solve the equation on the equator, the same equations on the equator. And this is baffling. Why don't the equations, where did these new solutions, or where mid-latitude solutions diverge from the equatorial solutions? And the equatorial solutions were done in 1966, so we know them for, it's not something that we learned about, 3 years ago. They have been here for close to 60 years, over 50 years, and they are the cornerstone, perhaps, of tropical dynamics, these solutions by Matsuno from 1966. And the sine and cosine solutions that we have here in terms of y will never approximate the Hermite function that are the solutions on the equatorial beta plane. So somehow the solutions on the mid-latitude, what I showed you now, are divorced entirely from the solutions on the equator, which is a bit baffling. Why not? Why, if you just want to look at the equations, Okay, see here, if you send F0 to 0, so what? Nothing really happens. Okay? You are left with beta y, and you lost a parameter. But it doesn't introduce singularities into the equations or anything fancy in terms of qualitative change in the equations. So why is there such a qualitative change in the solutions? Okay, are you with me now until now? Or have I lost some of you? I think you are right. But I'm quoting to you what people have taught for 50 years in classes, and it's very worrisome. Moreover, I'll tell you where the two solutions split in just about maybe more than half an hour. Okay, so the idea is to go back and try to look at the equations in a little more systematic manner. Okay, so again, this is the picture we had. H is constant, and these are the equations. Sorry, I didn't remember that I had the same equations here. I went backwards instead of going forward. And the question is, what can we do about these equations? And the answer is we can do several things. Number one, we can scale them so that many of the dimensional parameters will disappear from the equations. So we deal with fewer parameters. So we scale length on A. Remember that beta varies on the length scale of Earth's radius. Okay? So we scale all lengths on A, the radius of Earth. Okay? Just the only length scale we have it's not the only length scale, but it's a length scale we have in the problem. Time, we scale on 1 over 2 omega. Remember, I showed you that F0 was 2 omega times sine phi. So I'm going to leave sine phi in the equation so we can identify where the F0 and beta are located and use only 2 omega as the scale for the time. And therefore, velocities are going to be scaled on 2 omega A. And if you look at, and eta, this eta here will be scaled on the total height. It's linear. Since this equation is linear, we can just take H out and put it here. And I'm just noting that the non-dimensional y is actually the change in latitude because it's y over the radius of Earth. So if you look at the arc that spans delta phi in terms of latitude angles, divided by A, by the radius, and it's exactly that distance, the arc length, the length of this arc. So our non-dimensional y is exactly the delta phi, the change in phi. The other thing we can do is assume what is promised or what we can rely on, which is decomposition of the solutions into harmonic functions of x and t, since there are no coefficients, none of the coefficients is x or t dependent. Since there are no time and x dependent coefficients, we can assume a propagating wave in the x direction, which we cannot assume for y because we have a y dependent coefficient there. So c is the phase speed, and omega or sigma is the frequency. And then once you do that, remember this equation, top one, does not have a y derivative in it. It only has x and t derivatives, but x and t derivatives are replaced by multiplication by ik and minus ikc. And therefore, we can take this equation and express u as a linear combination of v and eta from here, v and eta, again, after substituting this, and substitute the expression for u from this equation into these two terms. And in short, we're going to be left with a system of two equations, two first-order equations for v dv dy here and the eta dy here. So basically what you have is an eigenvalue problem, two-dimensional eigenvalue problem in which you have two equations that, of course, are coupled for Vy, the V dy and the eta dy. I'm not going through the math, but you understand where we are heading. So these are the equations, okay? Trust me, I didn't err on the math. Sometimes I do err, but not this time. And we have the V dy equals a combination of V and eta, and the eta dy is also a combination of V and eta, which is what we should have expected because there are no nonlinearities, and everything inside of these equations, or of these coefficients, is what we know, either the sine phi 0, which is f, cosine phi 0, which is beta, and we have c, the phase speed, okay, of the wave, and the only additional parameter we have is this alpha, which takes care of all parameters or dimensional parameters in the problem, g times h over 2 omega, all that, 2 omega a, all that squared. So this is the dimensions of velocity squared, and this is dimensions of velocity squared, so it's non-dimensional, a single non-dimensional parameter, in addition, of course, to the waves that have k and c, or k and omega. Okay? So now we are in position to look at the solutions of this system, and as you'll see, it's not very simple, but if you know the background of what we know from 50 years, you'll see that it's not so difficult to somehow analyze what happens in these equations. So first of all, look at the case where when c squared is equal to alpha. When c squared is equal to alpha, this term drops. It equals to 0. And if this term drops, then we are left with this equation, but V has to satisfy two boundary conditions. But the first order solution of the first order equation will never satisfy two boundary conditions. Impossible, right? So therefore, the only way V can satisfy the two boundary conditions is for V to be 0 identically. Okay? So we set V to be 0, and therefore this term also drops, and we are left with the first order equation for eta, very easy to solve first order equation. But remember that now we have already satisfied the two boundary conditions of vanishing V at the wall. V is the normal velocity, so if we have a channel, then the velocity perpendicular to the channel is already 0 because V was assumed to be 0. Okay? So eta doesn't have to satisfy any boundary condition, and therefore it's a solution. Okay? It's a kosher solution of the shallow water equations. It's a very unique solution, if you want to say the general solution. But if you now look at what happens to the solution, it's 1 over c times the integral of this. This is f, non-dimensional Coriolis frequency. And what you see is that the solution decreases with plus y when c is positive. If this is positive, remember, f is always positive, at least in the northern hemisphere. And therefore, eta, the height, will decrease when we go in the plus y direction, and will decrease with minus eta when we go southward when c is negative. Okay? Very simple considerations, but as you'll see in a minute, it will show up. It will be a bit cumbersome. Okay, so these are the Kelvin waves. Remember, I told you that we have Kelvin waves in which V equal to 0. So the V equal to 0 waves are actually the null space of the eigenvalue problem. But it's not the null space of the shallow water equations, because the shallow water equations also have eta and u. Okay, are you with me so far? Okay, so Kelvin waves are a very special solution. If you stay here till Friday, you'll see that it changes drastically on a sphere. Okay? This degeneracy doesn't happen. I will say differently. This degeneracy only happens in Cartesian coordinates. Okay. So what happens with these waves is between u and eta, there is a balance that is what we call geostrophy. So U and eta obey the geostrophic balance. I'll show it to you in a minute. So this is in a direction perpendicular to the wall, whereas along the wall, what you see is just gravity waves that don't know at all about rotation. So it's a very, very, I don't know how to say it, specialized, degenerate, unique, what other words have I missed? Solution of the equations, okay? In one direction, there is a solution that usually typifies steady solutions, and in one direction, it doesn't know that there is rotation. Let me show you what it looks like, okay? So if we have a channel here, so what you see here is that the waves, the decay, the exponential decay in the direction either plus y or minus y, again, everything here is rotating. And of course, there is u that goes along with this change in C surface, but this is along. In the perpendicular direction, the u and eta are always in geostrophic balance. So let me go and say it a little more. Here's the frequency, that of gravity waves. So in this direction, it's like pure gravity waves. Perpendicular is geostrophy as if it's steady. And the amplitude decreases like exponentially. This is where the rotation enters. Of course, Kelvin waves, since they decay to zero, or if you will, they can only exist in a bounded domain or along a boundary. Without the boundary, you cannot have Kelvin waves. An exception is the equator, which acts like a boundary. You're not dealing with it, but I'm telling you that the equator has some characteristics of a wall, not two walls. Okay, and so the way the waves propagate is that in the northern hemisphere, the wall or coast is to the right, and in the southern hemisphere, it's the opposite. So if the waves propagate this way, and along this wall, they propagate this way. And again, very unique solution to the equations. Here is a somewhat more graphical representation. You see the decay. You see how the U reacts to the slope of the sea surface. If the sea surface is sharply sloping, then the velocity is large. And by the way, these along the coast, these waves correspond to convergence and divergence, which can cause upwelling. I don't want to talk about the implications of waves, but they are very important when you have boundaries, okay, in a bounded domain. Ooh, time flies when you have fun. Okay. In all other cases, again, the all other cases when C squared is not alpha, when the phase speed is not that of gravity waves, then the two equations I showed you comprise a genuine set of coupled linear equations. So let's go on. So okay, so we talked about Kelvin waves, and now there is no degeneracy, so C squared is not alpha, so we have two equations, and the two equations are coupled, and now we can eliminate one of the variables and get a second order equation for the other one, okay? So we can either eliminate eta and get a second order equation for V, or eliminate V and get a second order equation for eta. Since the boundary conditions are given in terms of V, it makes sense to eliminate eta in the from the set. And if you do that, you end up with this simple, very simple looking equation. So this is a second order equation for V. Why is it second order? Because it originates from two first order equations. Obviously, it's going to be a second order equation. And lo and behold, all the terms that are proportional to dV dy have disappeared. And in the equations, what we have is a collection of constants. And the collection of constants, we'll just call it the energy. And here you have a y dependency, a y dependent coefficient. So we'll call it the potential. Okay? So this is really a Schrödinger equation, okay, in which the potential is simply given by this f, the rotation, okay? Y sine phi 0 plus y cosine phi 0 is exactly f, non-dimensionalized. And therefore, f squared is the potential of this equation. And it's a Schrödinger equation. If you really want to make it look like a Schrödinger equation with the h bar, just multiply by alpha and put it in here, and that's going to be it. But it has the structure of a genuine Schrödinger equation. Okay? And the question is, number one, all the issues I raised in the beginning, we'll now have to sort them, solve this equation in various cases. Not all of them are analytic, but some of them are, and continue with the comparison with the classical theory, and again, how it degenerates to the equatorial theory, etc. Okay, but all our solutions are going to be given in terms of this form of a Schrödinger equation where the potential is given by f squared, or f is the rotation is the potential. So without rotation, then this will probably go away, and this will go away, and we'll be left with something like gravity waves or so. Okay, so just by analyzing the equation, we know that there are infinitely many, for each potential, no matter what you put in here, we have an infinite number of energy levels or constants that appear here. We'll call them energy. And each one of these energy levels is associated by the cubic equation that you see here, the relationship between E and C with three C's, okay, three phase speeds, okay, which is a reflection of the fact that our original system was three-dimensional in T. We had du dt, dv dt, and dA dt, so we had three d dt's. That's why now we have three C's, or three omegas, okay, three frequencies. And E appears here. Actually, it's the excess of energy over the minimum of the potential, to be exact. Mathematically, I'll drop this. It's absolutely correct, but not important for our purposes. So if we knew how to solve this, when we know how to solve this equation exactly, we immediately get three C's. Okay, and remember, the two Kelvin waves, we somehow sorted out as the null space of the eigenvalue problem, because V was 0 for Kelvin waves, okay, not U and eta, but V was 0. And now when you talk about the real space of solutions, we have two more, if you will, type of waves. One of them is slow, the Rossby waves, and two are large. I'll talk about it in a minute. Okay, and but let me go back now and see where do we diverge from the original work by Matsuno in 1966 on the equatorial beta plane. And what you see here now, if you set phi 0 equal to 0 in this equation, in other words, you set f0 to be 0, then this term drops out. This becomes 1, so you get exactly y squared here. This becomes 1. And the equation becomes exactly Matsuno's equation with the Hermite functions. If you ask yourself, where does the mid-latitude dynamics diverge or splits from the equatorial dynamics, the answer is right here, right at this point, okay? If you set sine phi 0 equal to 0, you are in the equatorial dynamics, okay? Why? Because you have here a y squared term, it's the Hermite, or the quantum mechanical oscillator, solutions of quantum mechanical oscillator. And this is precisely what Matsuno studied. If this is not 0, if sine phi 0 is not 0, then things become a little richer in terms of the solutions. But regardless of when we can solve it analytically, or for what values of the parameters can we solve it analytically, we can always solve it numerically. Numerical solutions are fairly easy for this equation. You just take an integration, you integrate from one wall to the other, match them, and vary C such that the two solutions are continuous at the matching point. Okay, so I would like to show you how we get the two wave types. So let me start by transforming the equation a little bit. I don't want to vary the domain every time I change the width of the channel. So I'm going to define a parameter that varies between -1 and 1. Not a variable, I'm sorry. Z will vary always from -1 to 1. So the width of the channel will enter now into the coefficients in the equation. If you do that, then you get this equation, okay? And the eigenvalue, the boundary conditions are set here, just a massage of the equation, okay? The sine phi 0 became 1. Remember, if you drop the 1 here, it's exactly Matsuno's equation, but I never dropped 1, so I did it when we still had sine phi 0 there. But the parameters, this epsilon is this E is now just a derivative of what we had before. This epsilon here is the H bar in Schrödinger equation, and this B, which is the beta effect, is just the width of the channel times cotangent of phi 0, which is the maximum change in the Coriolis frequency over the mean value. Okay, so B is usually less than 1, but it doesn't have to be very much less than 1. It doesn't have to be tiny. Okay, so I just redressed this wonderful bride with a different dress. Okay, that's it. It's nothing more than that. Okay, so now again, it's a linear, very simple potential, if you will, for this equation. Remember this E. I'm not going to go through the math, even though it's a class, but I just want to talk about qualitative, before I show you the solution, just qualitative conclusions from this formulation. Just by formulating it in this way, what we know is for each epsilon and B, for each pair of these two parameters, we have an infinite number of E, of energy levels, regardless of K and C, and analytical approximation can somehow be, I'll show you how we do some of them, and I'm sure smart guys in the audience can do even better than that. Now we have 3 C's. Remember I told you there's a cubic relation between the C and the E. Okay, the C and E are related by a cubic relation. So if you now look at the cubic relation, you look at the small C limit, okay, where C is very small, then what you get is this relation. Just drop the C squared term from the relation, and you get an approximation for one of the roots, the small root, and it's indeed negative, and it's indeed exactly what we showed you in the first slide. It's this, remember, this is beta dressed up in a different, this is exactly the zonal wave number, and again, it's dressed up in terms of E and not in terms of K and channel width. And if you look at the large C solution, you drop the 1 over C into the C squared, you get the 2 Poincare or inertial gravity waves. Now they are given by this combination of the 2 parameters, alpha and K. V, of course, equal to 0 gives us the Kelvin waves. I want to emphasize that what we see here, when V is 0, then C squared is alpha, etc., and eta is not 0. We talked about Kelvin waves. But I want to emphasize that the eigenfunction is identical. It's not similar, it's not close to, it's identical for both ways. Both inertial gravity and Rossby waves, the eigenfunction is the same. Okay? It's the same solution in terms of the eigenvalue problem, only the approximate solution for C is slightly different. I can just write it's 3 roots of a cubic that have these approximate solutions. They're very good, by the way, because the phase speeds are separated from one another very, very well. Okay, so just a little bit of some mathematical exercises. In the case when B equals to 0, remember when B is equal to 0, then the potential is just 1. So this potential well in quantum mechanics, we know how to solve it, okay? This is our potential here. So easy to solve this equation, right? It's standard way. The ENs are always larger than 1. This is always has to be positive for the solution to be satisfy the 2 boundary conditions. And this is the value of En, 1 plus something. And no matter how small epsilon is, you always get, this is always positive, so E is always larger than 1. This is going to become, in a few moments, it'll become important. And of course, we have 2 values for the phase speed. If you look at Rossby waves, you plug in this value of E, you see exactly the solution we had before, which is right again, beta here. For C, it was beta. For omega, it was beta k. Here we have k squared. Here we have the L squared, if you will, the wave number in the meridional direction. Again, quantized because we have boundaries. And here, this is again the radius of deformation, which is here in this context, it's sine squared, again coming from f squared over alpha in the non-dimensional. But again, the eigenfunction is identical for Rossby and for Poincare wave. So for Rossby wave, we get an exact solution for this case. Another case in which we have analytic solution is the case when B is equal to 1. And it's easy to explain to you why, because this potential 1 plus 1 times Z is symmetric about -1. Okay, so even though our domain is -1 to 1, if you extend the domain, like double it to -3 to 1, then you get symmetric. So all you need to take is the odd solutions of Hermite equation or the Hermite function solution for harmonic oscillator or quantum mechanics. And in short, remember that for n equals 0, you get 3 epsilon for E. It will become significant in a moment, okay? And it's an exact solution. And again, if you look now at the values of C, again, I plug it in the same equation. This is what you get. No need to talk too much about it. Okay, so just to show you what I meant when I talked about the, this is one special case, B equal to 0. Okay, this is the potential as a function of Z. It goes, this is B equal to 0. This is B equals 1, which if you continue artificially to -3, it becomes symmetric, so we can apply again the harmonic oscillator solution with the Hermite functions and get another value for another solution for E. And so we get 2 basic solutions for the eigenvalue, for the energy level of the Schrödinger equation. But as I told you, we can, okay, so let's just say a few words. Each mode has an eigenfunction, of course, and energy. And Rossby waves differ only by the C's, okay? There are small n negative C for Rossby waves and large positive and negative C's for Poincare waves. But other than the 2 C's, there are 2 different C's, they are identical. Okay, so the U and eta are derived from V by C, and therefore U and eta will, of course, be different. They're not going to be identical. But in terms of the eigenvalue problem, they are exactly the same solution. Okay, and for B equal to 0, there are no known solutions to the equation. But as I told you, we can solve it numerically and derive some analytic inferences. So here is the first eigen energy level, E0, as on a plane of epsilon A beta, so and B, sorry. And these are contours of equal values of this E0. Okay? So what you see here is that for B that's not 0, we can have energy levels that are smaller than 1. You remember, energy level of 1 typified the what we had here when B was 0, at B equal to 0. So right away you can realize what this theory does for the C's, for the phase speeds. It introduces energy levels that are smaller than 1. Remember, the energy appeared in the denominator. So if the energy is smaller, then the phase speed becomes larger. So the phase speed of Rossby waves that we can expect in this theory should be larger than the phase speed of Rossby waves when you set B equals to 0, which is the harmonic theory. When B is equal to 0, we get the harmonic theory when you have sine and cosine. If we just zoom in on this, okay, and one more thing, once epsilon becomes large enough, and large enough in this case is point something, okay, 0.3, 0.4, 0.5, then the contours becomes horizontal, which means that B has very little effect on the value of E. Okay? So it has to be small e and large B, if you will, for the two theories to be different from one another. Zooming in on the small epsilon, you see here that again, you see one cuts in here, but you can have much smaller values than 1. And again, remember I told you that when n equals 0, then we get 3 times epsilon. So this is epsilon of 0.2. Then here what you see is again E of 0.6, which is again 3 times epsilon. Okay, so I think I would like to go into one more step in the theory, and then I'll let you guys breathe some fresh air. As Lord Kelvin said in a statement like over 120 years ago or so, if you cannot express your thoughts in some concrete terms, then you've remained in the beginning of knowledge, stage of the beginning of knowledge, and not the stage of science. In other words, if we want to advance from the beginning of knowledge, from knowing something about anything and doing something with it, we should now provide expressions. I showed you numerical solution. I showed you some analytic solutions. The question is, can we do better than that? If you want the reference for this saying by Lord Kelvin, William Thomson, here is the exact reference. So what I want to do now is want to take one step further into the analytical solution of the eigenvalue problem I showed you before. Okay? I didn't talk at all about the eigenfunctions. Okay, so we seek expressions so we can advance from the stage of beginning of knowledge to the stage of science. Okay, not only find numerical solutions, mathematicians here will very seldom call numerical solutions an exact solution, right? We do. I mean, in geophysics we do, but mathematicians say, no, no. Exact is when you have a number, when you have an expression. Okay. So I want to draw your attention to the following fact. When we started, in the beginning of the theory, we expanded F to first order in Y, and we neglected terms of order Y squared. In the expansion of sine phi, you also have terms that are of order Y squared, right, or delta phi squared. But we neglected them. So for consistency, when we look at the potential, which is F squared, retaining terms of order Y squared is somehow contradictory with our essential expansion or first order expansion. We expanded to first order, and if you want to compute F squared, you cannot retain the second order term in F squared because you've already neglected second order terms in F itself, okay? So for consistency, we should drop out the beta Y squared term that we had in the potential. It's a subtle point. Will be less accurate but more consistent. Okay? You see what I'm saying? Is it baffling? Is it? Okay, so for consistency, let's just sacrifice the hyperaccuracy of the Y squared term. And remember, this was our equation, so I'm talking about this term. This is Y squared here. We are retaining Y squared term in the expansion of the potential, but we neglected it in F itself. So F also has in here Y squared, which we neglected, and this Y squared term in F will also appear in the F squared term. So what we're saying is, look, let's now forget about the Y squared term in the potential, not everything, but just the Y squared. So we retain the Y term. Okay? So we can now take this constant, put it into E and call it E star. And this term, we'll call it B, capital B, whatever you want to call it. Okay? It's just another dress. And seemingly we haven't done much, but we've done a lot, because now our energy level depends on one parameter only, and that parameter is B. Whereas beforehand, we had two parameters, epsilon and B, remember? So we got rid of one of these parameters. It doesn't really matter which of the parameters we threw out, as long as we understand that this is now perhaps less accurate, but it's more consistent. Okay? And it's much simpler to analyze, as you'll see in a minute. Are you all with me where I'm heading? Just, Yeah, here you have Y, according to everything I said up until now, we have Y squared. Correct. Cubic and also additional Y squared terms. Correct. So you cannot leave the Y squared term here if you expanded F to first order only. I understand. What I'm saying is, in order to be consistent, you should drop, because there is no question that now I'm accurate to first order. Yes, because I didn't include terms of order Y squared in F itself. Had I done it, I would have ended up in additional Y squared terms here. And cubic, you are right, and cubic, and fourth order terms. But The same way you neglected the fourth and third, you should also neglect the second if you didn't include the y-squared term in the original. And the proof is in the pudding. We'll just go ahead, do it, and see whether it works or not. Okay? So the idea is that now we have an expression for this B, here it is, and E star is just the E we had before, plus this term here. So here it is. And we have just different algebraic relationships, still cubic relationship between C and E star. So where is the gain? What the gain is now that I have to compute E star as a function of B and not E as a function of B and epsilon. So let's look at this equation. And I want to use perhaps not very accurate, but more accurate than dropping this altogether. Remember, in the classical traditional harmonic theory, you drop this at all. I'm only dropping y-squared terms. The harmonic theory drops this term altogether. It stays with beta, with E star and solves it, which was in the previous slides, we had E minus 1 as our eigenvalue. Okay? So I'm more accurate than the harmonic theory and consistent. So being more accurate and consistent is all we can ask for. So what can we do with it? So the idea is that if you look at here, at this equation, what I really want to do, and I'll show you how to do it, is to have this as the same as the variable here. So I would like the equation to read something like, something like this, okay? So the second derivative here, minus z, okay, I cannot get rid of y, times v. Why do I want this? Because this is a known equation. It's an Airy equation. In order to get from this equation to here, all you have to do is define z of y as this combination. Okay, so there is a transformation from y to z, okay, z or y to z transformation that leads you transform this equation into an Airy equation. And now, with an Airy equation, we can now do analytical work or solve it easily. How do we do that? So just, I'm sidetracking to just, I'm not sure everybody knows what Airy equation and Airy solutions are, Airy functions are, so allow me to share with you the frustrations I had. So if you want to really know what happens with Airy equation, first of all, you know that like any second order equation, it has two linearly independent solutions, okay? If you want to know the characteristics of these two solutions, think for a moment about this z as a constant, for a moment. Okay? If this constant, this z, is positive, then the solutions are exponentially decaying or growing. If it's negative, if it's negative, then we have oscillatory solutions for z. Right? Now, in Airy solutions, it's very different. They're not sine and cosine, and not exponential, but they carry very similar characteristics. The two solutions are AI and BI, and what you see here is for negative z, both are not perfectly, they are oscillatory but not periodic, okay? Oscillatory in the terms that they go up and down, up and down. It doesn't mean that the amplitude is constant, and of course, this is because this is not constant, and it doesn't mean that the spacing between the zeros is fixed, like we have in sine and cosine, where it's always pi, okay? But the characteristics, or these waves are actually oscillatory in the negative z, not plane, but line. And when you go to positive z, the two solutions are, one of them decays faster than exponential, and the other one increases faster than exponential. These are the characteristics, what characterizes the two linearly independent solutions of area equation. Okay, this goes back to maybe the beginning of the 20th century. When did people research? Abramowitz and Stegun summarized it all in 1970s, right? So it must be prior to 1960 or so that people knew about it. Yeah, but I think the research on his, it's the reason. When did people know about this? I'm not sure, but they knew about it probably anywhere from 1920s to 1970s, definitely, somewhere in between. And I think the theory developed a little bit, bit by bit, okay, not all of it in one shot. But all I'm saying is, look, if we now say, remember, we have two walls, and V has to vanish at those walls. So why don't we place one wall here and the other wall at the zeros of this area function? That's going to be a perfect solution of our eigenvalue problem. All I need to do is place, instead of two walls at two zeros of the sine function, okay, n pi and 2n pi, 1 pi, 2 pi, 3 pi, I'm placing the zeros, one somewhere here, I don't care exactly where, and the other one right here at the zeros of, these zeros are tabulated. We know what they are. Like we know what pi is. Okay? So all I need to do is make sure, number one, that my walls are located here. And if the wall is located here, in order for the function that's made up of the sum of AI and BI to vanish, the contribution of BI must be very, very small, very, very tiny. So even if you take just 2 in here, the combined solution of AI and BI has like 1,000 AI plus 1 maybe BI. So there are several orders of magnitude difference between the contribution of BI and AI to the solution. Okay? So if you do it, I'll send you the math and just show you the end result, and I think that's going to end today's lecture. When we do harmonic waves, okay, then the solutions are sine of n pi over L plus y, something that vanishes at the two channel walls. And the dispersion relation for Rossby waves is this. If you just go through the math, if you go to the trapped waves, then the meridional amplitude varies like AI, again, with this argument. B, remember, it was the beta, but dressed up in some fancy clothes. And this is the zero of the area function, the zero number n of the area function. So it's like, think about it as n pi. It's not pi, but you know, it's 2 point something and 4 point something, etc. We know the numbers are tabulated. And this is a function of beta, and their dispersion relation is this. Okay? And this B is given by that combination of dimensional parameters or something that looks like this in terms of the radius of deformation and Earth's radius. And the two behave vastly different from one another, and the condition for the validity are this will work only when we have a sufficiently large range of y such that I can really enjoy the z equal 2 or z equal 3 asymptote and the negative z. So it has to encompass a very wide range in y in order for this solution to apply. This, of course, applies everywhere because it doesn't care where you are. It just assumes that this is happening. Okay? This is the solution. And this solution indeed vanishes, but we know the inconsistencies associated with this solution. I want to go further at that point. Okay. Maybe I'll come back to it tomorrow. So So the condition for the validity of this theory is that the domain, this L, becomes larger than this arbitrary number where I chose the location of the northern wall of the channel, or far in, what we call infinity, very large. So 2 is very large. Why is it very large? Because the BI is already something like, I think, 1,000 maybe, and BI is much less than 1. So we can eliminate the contribution of BI. So what we have here is a definite condition of where the harmonic theory will definitely not apply. Whether it applies when this term is slightly violated, like if it's a little less than that, is a different matter. We'll check it numerically. But at least I now have a number when I'm telling you, look, if you have a channel that's wider than this number, and again, this B is a combination of the radius of Earth and the radius of deformation, etc., of the parameters in the problem. But if your channel is now wider than this, then you'll get no solution. Your solution will fail. Okay? What happens when it's slightly beyond that? Which theory applies? I think we'll see when we do the numerical simulations. Okay? So it has to be further examined. But at least we now have a concrete number that we can apply to see which theory applies where. Okay, I think I'm done for today. I thank you for your patience and endurance, and